We are Team 2014. We're working on software-defined based secure wireless networking. Our sponsor is United Technologies Research Center, and we're being advised by Dr. Shengli Zhou. My name is John Kaminsky.
My name's Amit Potdar.
My name is Bowen Liang.
We're all electrical engineers.
All right, the goal of our project is to develop a security algorithm using software-defined radio for wireless communication network. The network is intended to work in short range for implementation on aircraft.
So our current task in this project is to explore security issues related with wireless communication systems, and we're going to be developing a security protocol that will allow two radios to establish a secure connection between each other. And this is piggybacking off of a previous project done last year, where they implemented a Zigbee network, which is the IEEE 802.15.4 protocol. So we'll be creating secret keys between to establish a channel between the transmitter and receiver.
Man-in-the-middle attack is an attack where the attacker using eavesdropping and makes independent connections with the victims and relays message between them to make them believe they are talking directly to each other over a private connection, which in fact the entire conversation is controlled by the attacker.
So our solution is to do secret key generation via channel program. When a connection is established between the two radios, each radio probes the channel using a common message signal to estimate the channel and state information. After that, an encryption key is generated based on that gathered state information, and the average power at each carrier is computed across the spectrum. And at each carrier is assigned a 1 or 0 based on if it's above or below the mean to generate a secret key.
So for our technical approach, this is an example of what our template signal would look like. So what the common message between the transmitter and the receiver is. We're choosing equal power across a 3.2 megahertz bandwidth at the baseband frequency. We're going to be transmitting it at 2.48 gigahertz, like in the Zigbee protocol. And each of these carriers that we have here will be spaced 50 kilohertz apart. Here's a high-level system overview of what we'll be doing. So we'll be transmitting from an SDR sink to an SDR source. So that's the transmitter and the receiver. You'll receive the signal, and we'll process the channel state characteristics offline and also do the secret key generation offline. So here's our experimental procedure for what we have been doing. So our transmitter will send the common message. Once the receiver senses that message, it'll transmit the same message back. We'll compute the channel characteristics recorded by the transmitter and the receiver, and we'll compare them by computing the Hamming distance between the keys to make sure it's low enough. And then we'll create a new channel by changing the environment around, repeat steps 1 through 3, and we'll measure the Hamming distance between the secret keys generated between the two experiments to make sure that they are in fact unique.
So due to the current COVID-19 situation, our experimental procedure had to be changed, where we are no longer have access to the National Instruments LabVIEW Communications Suite, and we have to port everything over to GNU Radio, which is a free open source SDR platform. So since March, the bulk of our work has been learning how to use GNU Radio and learning how to implement everything in C++. And so we currently have achieved preliminary results, and our final results will be completed by May 6th.
So here's just a quick overview of our GNU Radio setup. The bulk of the work is going on in this block titled Convolve FF. And that's the block that computes the correlation with the incoming signal and the template signal to sense the message and then transmit the message back. And then on the right, you can see this is the setup here in my dining room because of COVID-19. And here's some experimental results. So the orange is the signal from the receiver to the transmitter. Blue is from the transmitter to the receiver. They're similar in shape, but have a little bit of a different amplitude. But when we generated the secret keys, they had a Hamming distance of 5.
So before the end of the semester, we want to be able to fine-tune our GNU radio implementation to decrease the time between our transmitter and receiver transmissions to get a more stable channel. And we also want to compute secret keys for multiple scenarios. Right now, we just have the one setup shown earlier. And later iterations of this project, possibly done by other senior design teams in the future, can also implement this algorithm in the wireless communication network set up by last year's team.